All right, thank you so much. I hope everyone can see the screen. And with that, I'm going to start with our full paper presentation titled Structural Text Segmentation for Legal Documents. So this is an equal contribution work between myself and my colleague Satya Almazian. And we have further collaborators Sebastian Lackner and Michael Gertz, also from the Database Systems Research Group in Heidelberg University. So to start with a brief motivation, what is structural text segmentation and especially given legal documents all about? So what we usually deal with in especially legal domain, we have plenty of unstructured document formats, for example, PDF documents. On the right, you can see one example of an end user's license agreement. And so if we look at this document, we can already see that it provides us with a natural segmentation of the context, right? So we have these paragraphs and then even like the headings with a different numbering provide some overview of how we as a reader should interpret this document. However, this kind of structure usually gets lost when we're dealing with a machine readable format. And even when we try to apply segmentation methods afterwards, usually such a paragraph or a document structure is lost. And why is this important? Well, especially for the segmentations, we have a lot of tasks nowadays, for example, in the workshop at this conference, where you're dealing with paragraph retrieval. So having like structured and thematically similar paragraphs is essential. You also have use cases for mergers and acquisitions, or last but not least, document search in general for just cases at like courts, meaning that once we can make sure that a segmentation of a document is still improved in a machine readable format, we're going to have a much better downstream performance, hopefully. And to illustrate this even more is even if we have some completely nonsensical text like a lorem ipsum example here, we're still going to interpret this as a semantically coherent unit, which is very important for our actual work here, because what we're now doing, and specifically comparing to previous work, is instead of focusing on a segmentation that bases itself just on a sentence level, this has some major problems. Specifically, there is a very narrow context given just by using a single sentence as a boundary. And the other question is, if we already have these thematical units like a paragraph, is it even useful if we split at a lower level, meaning the sentence level, than the paragraph level? And when we look first into this, specifically for the legal domain, there is a lot of hurdles that come with using existing methods. If you're looking at learning-based approaches, they usually come with custom architectures, which have like restrictive transfer learning capabilities. Most of them are some kind of hierarchical LSTM model, which is very difficult and unstable to train. You have exploding and vanishing gradients. And last but not least, they usually require large amounts of training data, which is not available in domain-specific applications such as the legal domain. And I think actually one of the major limitations that we encountered was not just using tools, but finding some of them. So they are really hard to come by. They either have no documentation at all, they are outdated. We had like one of the repositories that we tried to use that had only 20-year-old C code, no updated version was existing out there. And that was the most common scenario, actually, we weren't able to find any code at all. So even if I wanted to apply this to a legal document, I would not have any working solution at the moment. And so this is where our work comes in with its core ideas. And so we have these three main areas that we're going to focus on. So the first one is relatively trivial in understanding what is happening here. We're simply moving the attention span of our segmentation model from a sentence level to a paragraph level. This gives us a much more natural transfer of what elements are existing in the text already. And they kind of serve as a natural boundary that we assume in our work. Similarly, this also introduces a much broader context window, which can be helpful for methods that rely on this contextual embedding. And last but not least, paragraph structures are also something that we can semi-automatically extract from documents that have some vague annotations such as XML or HTML. The second step is actually more on the model for the segmentation itself, where we rephrase it from a purely sequential document segmentation, where you have one input sample of a entire document to a pair of binary classifications, meaning we simply look at two subsequent paragraphs and predict whether those are actually thematically coherent. This makes it much more easy to train. This is more stable and has less problems of an architectural sharing. And it is comparatively cheap in that we can use pre-trained checkpoints to actually use existing models and retrain them to our purposes. Given that we now have a different model formulation, we also rely on a different sample generation. And we actually present two different strategies in this work that make it very efficient to sample from a small number of documents even, and that can generate many more samples than the number of documents that are available. We're going to talk about this in more detail, but first I want to just again reiterate from a theoretical point of view what exactly we mean by structural text segmentation. And so what we assume here as an input is usually some kind of document that has a natural structure in terms of the paragraphs here. And indicated here with the colors, we have first 3 paragraphs that are topically coherent, and then a 4th paragraph that is covering an entirely different topic. And now basically the task of structural text segmentation is to generate this labeling in the terms of colors that we do not have a priori. Again, what I already mentioned is that traditionally you would feed the entire document as one single sample and generate one single prediction for this entire document. This is already where we have the mentioned problems of long-range dependencies. So the question becomes, is it even relevant for the 4th paragraph what happened in the 1st paragraph? And to exemplify this, in reality, you will have documents that are spanning several pages. And here really the context loses its meaning beyond just the immediate neighbors. Another downside again mentioned was the hierarchical training setup. To deal with the embeddings of single paragraphs and then predict over those paragraph embeddings again, you require usually very convoluted architectures that were used in related work that we try to abstract away here. So this is our rephrasing of the segmentation as a binary prediction problem called same topic prediction. And essentially, we make some form of Markovian assumption. So instead of relying on the entire context for the document, we just say, okay, we are training a classifier to predict whether 2 adjacent paragraphs are belonging to the same topic. Given our same sample document shown on the previous slide, what now happens is instead of a single forward pass, we're going to do at inference time 3 different predictions where we ask whether the first 2 paragraphs would be of the same topic, where the 2nd and 3rd paragraph are the same, and consequently the 3rd and 4th paragraph are of different topics. So this immediately removes the overhead of the sequential nature that I've previously mentioned. And the other point is, if we look at how those samples are basically laid out, just having the neighboring samples, it becomes relatively trivial to just sample many more pairs of paragraphs from the same document. Again, just to highlight, we can still apply this to the entire document sequentially when we're doing inference later on. Okay, so now to the actual methods used in this work. I'm sure you've heard plenty about transformers this week already. I just wanted to mention why we use this specific architecture here. And there's a few points that we thought made sense from our standpoint. Firstly, those come as large and pre-trained architectures, meaning that we do not have to worry about long and expensive training ahead of time. And especially since we can continue from those pre-trained checkpoints, it is much easier to achieve state-of-the-art results. For the fine-tuning as a binary classification task, the architecture basically looks like this, that we feed in 2 separate paragraphs as a single sample, separated by a special token, and will retrieve a class label that is then the prediction of whether those belong to the same paragraph or not. A small implementation detail here, we're actually using Roberta because they have slightly improved performance on all tasks, but we have experimented with BERT as well in this work. Our second methodology is the so-called sentence transformers, which was introduced by Ramis and Gurevich. Specifically, this is a variant of the transformers, which uses this bi-encoder layout. And if you again look to the figure, what happens instead is that we're feeding only one paragraph in a forward pass, and then retrieve these embeddings U and V, and basically predict based on the comparison of those 2 embedding vectors U and V. The main advantage is that SentenceBERT performs extremely well on embeddings and similarity tasks, which is shown in the original paper. And the more important aspect for our work here is that it also effectively doubles the input length. Because remember that for the BERT model, we can only feed 2 paragraphs in one pass. Getting back to the actual sampling of our training instances, we have two main strategies here. The first one is called random paragraph. And what we always do is essentially we sample from a reference pair, here denoted in purple, both a positive and negative sample. In the instance of random paragraph sampling, what we do for the positive sample is, or for both actually, we just aggregate all of the red paragraphs into one class and sample a random positive pair from this same topic. Meaning that this can also come from another completely different document that has the same topic in it. The negative pair, similarly, will sample from all of the paragraphs across all documents, but from a different topic. And that the problem of this method is that it requires some cross-document normalization, where we basically have to actually normalize here and verify that these sections are actually the same across different documents. The improved strategy that we use as the so-called consecutive paragraph sampling, the name is slightly misleading, but essentially what we do is we restrict ourselves by just sampling from the same document one in this instance, where both positive and negative pairs have to come from within the same document, but however, still from either the same section or a different section. The main advantage is, again, that we now no longer require any cross-document normalization, which makes the annotation process for our initial training setup much, much easier. However, there is this one remaining question that we also want to answer in the experiments, that is whether it generalizes well to unseen topics, because now we do not have any relevance between the documents, which might lead to a much poorer generalization. Talking about the dataset that we used in this experiment, we actually obtained a new terms of service dataset from website terms of services. So the main point being that terms of services always have to be available from the landing pages directly, making them relatively easy to extract. And the other benefit is that while they focus on a legal context, they have relatively similar structures and topics across many different documents. So we will obtain, for example, shown on the right, around 20,000 of the documents that have a limitation of liability clause in there. And similarly, we normalized all the other sections as well. This is only an excerpt of the most frequently appearing one, but there is many more because we extracted overall around 40,000 documents based on this Alexa top 1 million list of English websites, from which we then automatically extracted the hierarchical information that was available in their terms of services, which includes linking different paragraphs to a specific section. The one manual annotation that we had to do for our random paragraph sampling is the mentioned cross-document normalization. Specifically, limitation of liability usually was spelled in 3 or 4 different ways. You had limitations of liability or liability just as a single word, referring to similar topics that were manually grouped together. And after all the pre-processing, we're left with around 40,000 usable documents, depending on which task specifically we're looking at. The average length being around 22 to 23 paragraphs and around 3 sections. Now actually moving on to the experiments. So the evaluation that we did was firstly verifying that our binary classification actually works well, and then transferring this into an actual downstream segmentation task. The setup that you're seeing here are the basic methods that we compare for both the classification and segmentation. We will introduce further related work in the actual segmentation task. But for now, baselines that we used are simply averaging glove embeddings. In the previous presentation by Malte, we've seen that this usually leads to really good performance out of the box. Similarly, bag of words and TF-IDF vectors are a good approximation and turn out to be actually competitive with related work. But what we specifically are interested in is fine-tuning transformer models, where we choose a Roberta base model with a classification head, so the so-called RO-CLS model, and then a sentence transformer variant of the same Roberta base model called STRO. As a brief side note to the hyperparameters, we usually sample 3 positive and negative pairs from this per paragraph in the document. And we run all models from 5 different random seeds to account for any statistical variance in the training procedures. Training is performed over 2 epochs for the transform models, and generally our 80-10-10 split is consistent for training, development, and testing. Now, looking actually at the same topic prediction task performance, we compare both the different models and the different sampling strategies. One slight caveat to this is because we sample differently, both for the validation and test sets, we cannot compare models between random paragraph and consecutive paragraph sampling here. However, we will still be able to compare those on the next slide when it comes to downstream performance. What we will look instead is how these models perform across like the board, meaning basically we can still look at how glove averaging performs in comparison to the, for example, sentence transformer models. And we see that the sentence transformer models for both strategies perform extremely well, much better than any baseline, and specifically show a better performance, although only slightly better for consecutive paragraph sampling compared to the standard transformer models. Generally, what I want to highlight is also that random paragraph sampling seems to have some inconsistencies in the training stability, which can be due to a variety of reasons. However, we noted a large variance in the performance that was actually subpar to some of the baseline methods. Yeah, going on to the actual segmentation and then circling back to the tasks that we actually wanted to solve here. We have this traditional segmentation metric called the boundary error rate PK, which is frequently used in other segmentation works. It gives essentially a probability of two samples being incorrectly labeled when compared across the document. And this means the lower the error rate, the better the method is. Furthermore, we introduced two related works for which we could find working solutions. One of them is GraphSeg, an unsupervised method introduced by Glavash et al. That is usually also working on sentences. And similarly, Wikiseg, Koshorek et al.'s supervised segmentation model that was trained originally on Wikipedia data, for which we do a training from scratch to have no advantageous embeddings. What we can still see here, and which is consistent with our expectations, is that the consecutive paragraph sampling for every method performs significantly better than the random paragraph sampling. So specifically for the transformer-based method with this classification head, we see that the consecutive paragraph sampling is indeed more stable on the downstream performance as well, and almost competitive with the sentence transformer model from the both from the random paragraph sampling and consecutive paragraph sampling. Similarly, all of the transformer models, with the exception of the unstable Roberta CLS model, outperform the baselines as well as the related work. We do denote that while it seems that those results are extremely bad, this might be mainly due to the fact that they were originally designed to work with sentence inputs and not paragraphs, which is especially detrimental for the unsupervised method GraphSeg. However, for Wikiseg, we assume that there was also some implementation detail that we might have gotten wrong, leading us to the conclusion that those models would not have been usable by somebody trying to get segmentation on legal documents. Because we personally found this method to be rather hard to understand, what we also did is come up with an alternative evaluation metric for the segmentation, specifically on paragraphs, which is the so-called accuracy up to K. It's rather simple to explain. Essentially, we account for the fraction of documents that have less than or K mistakes. So this actually gives some relevance to our error rate seen on the previous page, because even though we tend to have rather low PK values, if we tend to look at the transformer models, which is this upper curve, even those have only around a quarter of the documents that were classified entirely correctly. Keep in mind, again, those are around 23 predictions that we have to do per document. However, if we account for only 2 mistakes, we can see that already 2/3 of the documents are classified correctly, which might make this still an acceptable segmentation for many downstream applications. But more importantly, it allows us also to give a generally more interpretable result, because even here we can see that the best performing baseline method, the average glove with consecutive paragraph training, is still significantly worse than the transformer models that we see here, with the one exception again being the very unstable Roberta CLS random paragraph sampling model that performs even worse than that. Just as a reference, before anyone would ask the question, we also just tried predicting what would happen if we just said, okay, all paragraphs belong to the same topic, which is the last red curve here, which is predicting simply just always the same topic. Yeah, and with that, we're coming to a conclusion of this presentation. So in summary, the main points that we introduced in this work is a simple but effective training strategy for document segmentation, specifically on paragraphs. We supply a new resource available to the community of web terms of service documents, and have shown in experiments that our proposed transformer binary classification models also translate extremely well to downstream performance tasks. As a brief outlook, what we can do in future work is essentially investigating the actual retrieval performance, specifically in long legal documents. So I've already mentioned in the introduction some of the use cases that might be applicable here. We're also working right now on a more general text segmentation model, which is trained on Wikipedia data, just to see how that compares, maybe also in a zero-shot setting with domain-specific data. And largely, we've already heard about other transformer models that have a longer input context, which might be beneficial for our training on paragraphs. So this is one of the options that we can pursue here as well. With that, here is a link to both our code and data, and as promised, you can easily use this model through the Hugging Face library. Feel free to check it out and give us feedback on our work. And with that, I thank you for your attention, and I'm happy to answer any questions that you have.
Thank you, Dennis. And now we have a question from the audience. From Sabina Wennert. Very interesting talk. I heard you had the data in a HTML format. Did you consider using any superficial cues, font size, boldface from the HTML in the addition to the text paragraph information?
That's a really good question. So what we specifically looked at, why we specifically didn't look at it, is mainly because we use some of this information in the extraction of the hierarchy. So to determine the order between different HTML documents, it's not as straightforward as it might sound. Some of them use the H1, H2, H3 tags, which is relatively easy to extract headings. However, bold facing was sometimes used as a replacement, or similarly the font size. So we use this in the extraction process, but we actually do not consider this for the segmentation here. The other reason for that is also because we want this to be applicable to not only websites, but also more specifically to any form of document that might not have a similar normalization. So I have worked a lot with PDF documents and can confidently say that even though you might have a larger font size, due to a different font, it might actually appear smaller. So this does not necessarily correlate to the actual interpretation from a human perspective here.
Okay, and you have another question. You make a reference to Wikipedia in the article, which studies terms of service. Both examples are sorts of texts that summarize information, organize them in a steep recipe. Such texts follow consistently a pattern of structure very different from, for example, Superior Court judges' rules. Are not those findings in structures limited to a more simple chaining of argument? Would it help too with understanding more complex structure?
I mentioned one of the main reasons why we use the terms of service documents is because we can confidently obtain a large number of documents, which is originally required to train our models here. I agree with you that those tend to follow a similar structure, and the problem is mainly that we do not have access to a large enough like supervised / annotated data set with complex cases. I would be very interested in this, and this kind of relates to the future work that we plan to do, where we evaluate an actual retrieval setting, or I'd say like downstream performance of our segmentation models. So yeah, I agree, but this is basically one of the limitations that our work currently has.
Let me see if I have further questions.
Maybe in the meantime, I can also add to this from a perspective of the related work that has done the training on the Wikipedia data, the Wikiseg model. In their own paper, they actually evaluate both within Wikipedia, but also have external training sets that are not necessarily more difficult, but certainly from a different domain. And even there, they tend to beat related work, or at least be on par in performance. So this gives us some hope that our model actually translates well to more complex cases as well.
Okay. All right. So we have a few minutes left. If you want to say a few more words, Dennis, make yourself comfortable.
Yeah, so again, thanks for your attention. And I think the main issue that we're like still looking for is a suitable downstream application where the segmentation can help directly. So if you do know of any shared tasks or specifically have your own connection that would collection of documents that would benefit from such a segmentation, feel free to reach out. And with that, I think that's it from my side. So thanks again for the opportunity to present here.
Now we have a question from the audience. Aline Macoin from Federal University of Paraná says, very interesting work on the automatic inference of topics in tasks. Do you think as a future work to identify if the tasks, besides having the same topics, can treat the subjects in the same way? This would be very interesting for analyzing court decisions.
Thanks so much for the question. So actually, there's 2 points that I want to address with this. The first one being that our main focus was less on the actual establishing of a novel task specifically for this inference. And so we mainly treat this segmentation as a pure pre-processing step to existing downstream applications. However, given that this question does actually bring up some nice points, there is 2 works that I can think of that kind of go in a similar direction. The first one actually takes this segmentation step a bit further and does automatically infer the topics or the topic headings, which they do on Wikipedia data. However, I think this can be relatively easily can be transferred to the legal domain as well. The work I'm referring to is called outline. The task is called outline generation in this case. I believe it's a paper from 2019. And the other task is what you're referring to as subjects. And I hope I interpret this correctly. Would be dealing with, I think, too narrow of a context. The problem here is that our main advantage is that we can automatically extract large amounts of data without any major labeling. However, if you do have such larger corpora, I think the closest that you could get is something like the EURLEX corpus from the European Union, which does provide you with, I think, about 50,000 documents, which might have enough samples overall to allow for a classification in that sense. However, in my opinion, the context with our paragraph-based method would be probably too big, and you would have to revert back to traditional segmentation methods that only treat an individual sentence, because only in that context, I believe that a subject is unique enough to perform some actual classification. How good the performance would be, I don't want to comment on. It largely depends on how many different labels you're going to have as a target value space.
Perfect. Thank you very much, Mr. Dennis, for your participation again and your brilliant work. And now, following the next presentation of the day. But first, of course, I'm so sorry. I would like to give you the stage again for last words. If you want to say thank you to anyone or
yeah,
anyone.
Thanks so much. I appreciate the questions. So really looking forward to have more discussions. If you want to catch up on this work specifically, I'll also be in GatherTown afterwards, after the session. And then I think I will get back to give more space for the short paper presentations afterwards. Thanks.